So just to get brief, extremely briefly to the main point, but we won't come back to this for quite a few minutes. Well, first to say that what I'll be talking about for the main part of the talk is with work with Song Sun, and what it's about to put this in an egocentric way is the last few years I've been giving talks about this kind of thing, Kähler-Einstein metrics and things, going back, I think, to Miles Reed's 60th birthday talk in 2008. And what I've often said is that the main problem in this subject is relating something in differential geometry, called Gromov-Hausdorff limits, to something in algebraic geometry, I mean, the study of algebraic varieties, in particular, whether one of these limits, which we'll come back to talk about, has in a natural way an algebraic structure. And I've been saying that this is the main problem. If we knew this, everything would be much simpler, but not knowing it, one has to try some more or less complicated things to get around the problem. So that the years go by, Miles Reed is now pushing 64, and things move on. So what I come here today to tell you is that I think this, that indeed these Gromov-Hausdorff limits should have algebraic structures, or at least some restrictions I'll talk about, and that we can actually prove that. So that's going to be the point of the talk. But I say we'll get on to all that in a short while. But let's spend a bit of time reviewing, at a rather basic level, a fundamental technique, the Hormander technique, which we're going to employ, of course, in this more technical discussion. So what I'm going to say for the next 5 minutes or so, or maybe more, will be extremely well known to many of the experts here. So what this technique has to do with is constructing sections of holomorphic line bundles. So we have a compact complex manifold X and a positive line bundle over it. So this has got a connection with a curvature minus I omega, where omega is a positive form. And what I want to say is that if we take large positive powers of this, that this has got many holomorphic sections, informally speaking. And so, of course, one well-known precise manifestation of this is the Kodara embedding theorem. So let's just review how one proves this by this Hormander method. So the first thing to say, is that taking a power of the line bundle corresponds naturally to rescaling. We change our curvature form, multiply it by k. That corresponds to scaling the metric. If we think about of course, we're going to think about this as defining a Kähler metric, as I said, on X. We're scaling the metric in the sense of lengths by a factor of root k. So k corresponds to root scale, length scale. So if we, it's a picture of our manifold, we're going to to work in the neighborhood of a point, what we first want to say is that when we scale up, the manifold becomes approximately flat, so that we can think of a small ball in the original metric, but which will become some large ball in the rescaled metric. So let's say we have an embedding iota from the standard ball in Cn. N will be the dimension of my manifold into X, centered at our particular point P that we chose. And we can, for simplicity, suppose that in fact, in our rescaled metric, this is actually an isometric embedding. So let's suppose the metric is actually flat in a neighborhood of P, for simplicity. That doesn't matter because, as we say, whatever metric we have, on a small scale, it'll look approximately flat. So we would just introduce some small extra error, which won't cause a worry. So now one says that on Cn we're just going to take with the standard metric, we take the trivial holomorphic line bundle, but of course the connection on that line bundle will have curvature the standard form, and so it would be non-trivial. And the sort of standard holomorphic section that you get, let's call it sigma naught, it's got the property that it's a Gaussian section, that the norm is something like e to the minus mod z squared over 4. So this is the key insight. For practical purposes, this is a kind of compactly supported holomorphic section, in the sense that this exponential decays so quickly. So we can, under this isomorphism we're supposed to have, imagining we have of the local structure, we can transport this section to think of it as defining a section of our line bundle when we've taken the power we want to get to the right scale over this little ball, the image of iota. But of course, that's only defines something here. What are we going to do on the rest of the manifold? What we do, of course, is we introduce a cutoff function. So with supported in this ball equal to 1 on the ball of radius r minus 1 or something. And then we're simply going to multiply sigma naught by this cutoff function. So we're going to just smooth it out here. And then we're going to extend by 0, of course, on the rest of the manifold. So with some simplification of notation, we're suppressing these maps we use for this transport. We're writing sigma 1 is equal to beta r times sigma naught on x. So when we do this multiplying by the cutoff function, of course we've done damage. This is not going to be holomorphic anymore. We do a d bar of sigma 1. But this is going to be very small, because this is just going to pull in the derivative of this, which is some size 1, say, but multiplied by sigma naught, which has got this exponential decay. So it's exponentially small in terms of r. R is a parameter we're going to choose suitably large. So the norm of this, whatever, any sensible norm we took, will also be order e to the minus r squared over 4. So very, very small. So we haven't succeeded because we haven't constructed a holomorphic section, but we've constructed an approximately holomorphic section in the sense that this error term is small. So what we do next is we're going to say, we're going to construct sigma. It's going to be, we're going to take sigma 1, and we want to correct it to make a genuinely holomorphic section, so plus minus eta. And Hodge theory tells us the formula to write down, or a sensible formula to write down to do this, provided we know that the H1 of our line bundle vanishes. That's to say, provided we know that the Hodge Laplacian, delta d bar, invertible, but if, so it's the same as on the place where this thing lives, the 0, 1 forms with values in L or L to the K, that's what we're talking about. Then the formula we should take is that eta should be, we take d bar star delta to the minus 1 of d bar sigma 1. Straightforward Hodge package to show that this thing precisely corrects the error term that we put in. So the idea is we want to, of course, if eta were equal to sigma 1, we wouldn't have got very far because sigma would be 0. I mean, we always know we have 0 as a holomorphic section. The idea is we want to show that eta is much smaller than sigma 1, so in fact we've got a non-trivial holomorphic section, and moreover one that we pretty much understand because it pretty much looks like the thing we made to start off with. So we do that using the basic ingredient is just the same as the standard ingredient in the standard proof of the Kodaira embedding theorem via a vanishing theorem. That's to say a Bochner type formula for this Laplacian. Delta d bar is equal to, let's just write, say, p star p, a certain other differential operator p, plus, let's write it this way, say the Ricci curvature over k plus 1. So it's the rescaled metric. There's always a bit of confusion here whether we're going to work with the original metric or rescale things, but I'll use the notation of working with the rescaled metric. So this is the Ricci curvature of the original metric. When we scale, that gets smaller. So that's why we put the factor of k in. But we've got this, what's for us a good term, 1. Yeah. And what is p? P is, you can think of it in different ways. One is, it doesn't matter too much what it is. One is that you can think that on this bundle, this one, you have a covariant derivative, and so you can split that into parts, 0, 1, and 1, 0 parts, and then p is the 0, 1 part of that. That's one way of saying it. Another, which leads to a neater calculation, is to use the same identification that appeared in Bo Banson's talk yesterday. We identify, as he said, multiply and divide by the canonical bundle of L. We identify this with the N1 forms with values in L tensor K star. And under that identification, P is just the D star operator, the coupled operator formed using the connection on this bundle. And then from that point of view, the Ricci term comes in from the curvature of the canonical bundle. In any case, this is the well-known differential geometry calculation which underlies sort of everything. So what we do is certainly when k is large, we had a compact manifold, so the Ricci curvature is just some bounded thing. We can make k large enough that this is less than a half, say. So what we certainly have is a norm of, what this implies is the operator norm of delta d bar to the minus 1 is less than or equal to 2, say. The operator, by choosing k large enough. So now, how does the calculation go? The norm of eta squared what do we have? So we take d bar star delta to the minus 1 d bar sigma d bar star delta to the minus 1 d bar sigma. We can put that across there to write this as d bar star, but that's half of the Laplacian. The other half doesn't matter because of the d bar here, so that cancels with the Laplacian. So we just get this is delta to the minus 1 d bar of sigma in a product with d bar of sigma. So this is less than or equal to 2 times the norm of d bar sigma squared, which is order e to the minus r squared over 4. So this is why, I mean, clearly the original thing we made had got norm roughly 1 or something, some fixed number. Why eta is much smaller, we make r quite big, and why we end up constructing an interesting holomorphic section. In particular, say we construct a section which doesn't vanish. Oh, right. So this is just an L2 norm, but then we have elliptic estimates in, say, B of 1. So here, in B of 1, both sigma and sigma 1 are holomorphic, so eta is holomorphic. So very elementary elliptic estimates mean that the L2 norm controls the L infinity norm. So we control L infinity norm. So in particular, say, the value of the function at 0, the point we started with, is not 0, but we can make as close as we like to 1, bigger than 0.99 or something. More generally, we could we can construct many more sections like this. If we take any holomorphic function f on Cn, say a polynomial, we can not start with sigma 1, but we can start with f times sigma 1 and produce a holomorphic section, which is going to be approximately equal to f times sigma in our little ball that we have. Little ball. So we construct lots of holomorphic sections, and it's just what the Kodaira embedding theorem requires. So that's yeah. This is our review of what's supposed to be well-known material. I mean, Horminder didn't actually. Horminder worked, as far as I know, in a slightly different setting of Stein manifolds and so forth. So I don't. But the basic idea is the same. So this must be a well-known idea for something like half a century or so. I don't know any textbook where this is done, surprisingly. I mean, lots of textbooks that do the Kodaira embedding theorem, but I don't know any textbook that does it this way, but it's, to me, it's a very good way of doing it. Because this is the point of the talk, well, this is a very robust method, which admits many modifications and so forth. So one modification, just to slightly digress, this is what I was vaguely planning to talk about today until a few weeks ago. But I'll just spend a few minutes discussing it. One thing we're interested, let's introduce a function which has appeared in various talks. So if we take rho k is a function given by the sum of the if we have any k, we can take an orthonormal basis of the holomorphic sections of this line bundle, take the sum of squares function. It doesn't depend upon the orthonormal basis. And that's an interesting function to consider and important in, we've heard in various talks why it's important and interesting. So for example, supposing we're interested in, what do I want to say here? So supposing we have our manifold. Let's slightly change our position. So here we said, well, we had a smooth manifold. We might as well suppose it's essentially flat in a ball. Doesn't really matter. But supposing we have a manifold where we have a well-controlled ball where it's after scaling essentially flat. I mean, so you start off with something of bounded curvature or something, you scale it up a definite amount, and it becomes pretty much flat. But supposing outside here we don't know anything. We don't have any particular information except for a bound on the Ricci curvature. All we used about the manifold was we need to make k big enough to kill the Ricci curvature. So supposing outside we just know that the Ricci, and moreover we have a sign. The positive Ricci curvature is good because that makes delta even bigger. So if delta is just, we just need a lower bound on the Ricci curvature. Then we can still, as far as studying sections which are sort of concentrated here in a sense, we can proceed just as before. It doesn't matter what's outside there, provided the Ricci curvature is controlled, we don't care because the method works. That's the sense in which it's robust. So in particular, so there's a fairly the theory of the asymptotics of this rho k function is local in the sense that if you have a good region, you can proceed. You don't care what happens in the rest of the manifold, provided you just have a bound on the Ricci curvature. So that was what the talk was going to be about, but not anymore. That's all I'm going to say about that. For them here. So this newer work is a bit different, as I'll go on to talk about. But let me say that the background to this is a slightly different project with which is some joint work with Su-Chong Chen. So let me again say just a minute or two to talk about this. This has to do with studying Kähler metrics, or specifically Kähler-Einstein metrics, with cone singularities along a divisor. So roughly one would like to prove all the things one proves about ordinary Kähler-Einstein metrics. I think we'd like to prove analogues for this slightly larger world. And by and large, you find, if you try to do that, many things just go through in a pretty straightforward fashion. But there's one kind of novel difficulty which occurs where you have a family of metrics in which two sheets of this divisor come together. I mean, let's explain in the two-dimensional case, simply, that if we take, so e.g., one complex dimensional case. Supposing we take a plane and cut out two wedge-shaped regions like this, and then glue the edges together in the manner shown, then what we get is a surface with a flat metric, but two cone singularities, obviously. But we have a parameter, which is this distance. And so we can write down a family, a model family of these flat metrics, in which this goes to 0, and in the limit we get something with a different cone singularity. So more generally, you can imagine the same kind of thing happening in higher dimensions. So the point of this is to show that, at least as far as the complex structure is concerned, what happens when these two sheets of the divisor come together, or many sheets come together, the background complex structure is standard. So we can really write the divisor, as I say in the two-sheet case. The model picture will be something like where the divisor is given by w squared is epsilon f of z, and we let epsilon go to 0 to get in the limit something with multiplicity 2. And is the model. So that's all I'm going to say about this, because it's a slightly different story, which we haven't so much written down. But this is important background to how the ideas developed. Right, so all this is preliminary. So now we can come back to the main. Now the main part of the talk begins, as it were. While I catch my breath, perhaps it's a good time to ask you any questions about. Well, in this higher dimensional version, well, it's we don't know. I mean, what we expect is if we have a picture like it's a kind of a picture, but transverse. If we take a generic point, transverse to here, it looks like this model, and around a branch point, there's a kind of a different model that you could write down. But that's what we expect rather than what we know how to prove. Knowing how to prove that is what we labor on. Okay, so the main part of the talk, this is going to feature slightly different, some different material. We've encountered the Ricci tensor in this sort of complex analysis guise appearing in this Weizenbott formula, that thing. But now we're going to encounter it in different ways, in a sense more classical ways, in Riemannian geometry. So let's just perhaps recall a bit about this. For example, we have Meyer's theorem. If the Ricci curvature is bigger than that for the sphere, so we're in real dimension 2n. So this is the Ricci curvature of the sphere of the relevant dimension. Then the diameter is less than that of the sphere. It's one well-known property of having positive Ricci curvature. Another is Bishop-Gromov comparison, which says if we take balls, define metric balls in the usual sense, and we look at the volume of this, so if Ricci is positive, say, I mean, there are different versions, but let's suppose Ricci is positive, the volume of the ball divided by the volume of the Euclidean ball, essentially r to the in dimension 2n plus 2n, is decreases with R, or weakly. So, of course, there are many more. We'll be mentioning many more sophisticated and subtle bits of theory, but these are sort of two fundamental and well-known things to begin with. So, what do we want to say? What we want to say is that this is the main result. This is the result. What we want to we're going to consider. We're going to stick to three complex dimensions. Let's consider Kähler-Einstein manifolds of a fixed topological type. In the obvious, what I mean is we have a fixed polarization. So such a thing we'll write as L over X. We have a fixed volume, for example. And a positive Ricci, well, non-negative Ricci curvature, let's say. And more technical, let's say non-collapsed. That's to say, the volume of any metric ball is bigger than some constant times r to the, well, n is 3 here, but that's right, 2n, for r less than or equal to diameter. This is what we want to consider. The case we're mainly interested in is where we have Fano manifolds. L will be the dual of the canonical bundle. The Ricci will be equal to 1. This non-collapse condition will be automatic as a simple consequence of the Myers and the comparison. Because we know the volume couldn't be too small because otherwise it would be the whole volume would be small. But if we state slightly weaker conditions, then we can apply what we didn't do to Calabi-Yau manifolds, for example, with this extra hypothesis. So what we're going to consider is this rho k function. So what we say is for any such manifold, what do we want to say? We want to say rho k. We want to prove a uniform lower bound on this rho k. That's what we want to say. So let's try and get it exactly right. So for all k naught, there exists a k bigger than or equal to k naught. There exists an epsilon k bigger than naught, such that rho k is bigger than or equal to epsilon k for all such x. I think I've said it right. So it's sort of a universal lower bound within our family. A universal. Once we make k big enough, roughly speaking, this rho k is bigger than something. So what it means is that there's a holomorphic section with L2 norm 1. It's got a definite size at any point. So this is a conjecture of Tian for the 90. I mean, in any dimension, this is a conjecture of it should hold is essentially a conjecture of Tian from the early 1990s, I think. And Tian has written about the importance of having something like this in these kind of issues I mentioned at the top. So there are lots of good. This is rather a technical result, but there are lots of good consequences of this, which Tian says should flow from having that, and we agree. But I'll say a little bit about the applications at the end. But for the main part of the talk is just to believe that this is an important thing to know. How are we doing for time? Yeah. the result is just for dimension 3, but one could hope the methods extend. I'll talk a bit about that, but this is just for dimension 3. So, what am I trying to do? Okay, time's pressing on. Where have I got to? Okay, so let's not talk. How are we doing for time? Not to talk directly about that for a moment. To give the main idea of the argument, let's go back to just to give a model argument. Let's go back to the situation we were considering before, and as we said, the proof is robust, so we can perturb it, and it will still work. So let's explain that. So we had our big parameter r. Let's suppose we also now have a small parameter delta. And supposing we know only that we have an isometric embedding, or essentially isometric embedding of not of a ball, but of an annulus inside X. So this is a model argument for the proof. So suppose we have iota from B of R minus B of delta goes to X. So we have this is our flat region we understand. We have an outside, it's called the exterior, which we're still talking about that. That's what we talked about before, roughly speaking. But now inside X we have an interior region as well. The interior, the component, the boundary, that face. So what we want to say is, just like it didn't matter what was outside, provided the Ricci curvature was controlled, it doesn't really matter what's inside there, provided the Ricci curvature is controlled. We can still do our method. That's because now we're going to introduce a cutoff function, say beta delta. Let's introduce another parameter. Actually, these are going to be called delta prime, what I've got. So let's say this is going to be less than half another parameter, delta double prime. So we're going to have another small, slightly larger region here. So let's have a cutoff beta delta primed. Which is going to be vanish on so equal to 0 when mod z is less than equal to delta primed, and equal to 1 when mod z is bigger than equal to a half delta double prime. So the basic point, but a very elementary point, is that we can, with small numbers delta prime and delta double primed, we can make the L2 norm of the derivative small. So to be a bit more precise, whatever delta prime I choose, I can choose a delta double prime such that whatever number I want this to be, I can make it smaller. That's what I wanted. So this is, I mean, if you don't know this, it's a simple calculation, a simple exercise to find such a function. Essentially, this is the fact that L21 does not embed in C0. We couldn't do this in real dimension 1, but in any real dimension bigger than 1, this is true. So what that means, lost a page. My notes. What that means is all we do is we hit the thing with another cutoff function. So now we're going to make sigma 1, everything just the same story, but now the formula is sigma 1 is beta delta prime times beta r times sigma 1. And because of this is the L2 norm, because of this property, we are still good for estimating the d bar, the L2 size of the d bar of this. So you see now we made a more drastic change. We have our sigma, but now we're sort of just cutting it off in what looks like a drastic way, but we can just Hormander it back into place with our method to get a section. Well, that gives us a holomorphic section. What about the estimate? What can we say about this section in the mystery region, in the inside where we don't know anything? So, all right, did I say what we're supposed to know? We have this Ricci bound, of course. But can we say anything about what this section does in the... Yep. But let's suppose, it's actually a little region, so let's suppose that the diameter of this interior piece is also small. It's less than or equal to 2 delta prime, or something, some small number. Then we can say something by a straightforward argument. I mean, straightforward for people who do such things. As I say, previously we had elliptic estimates in a flat background, so everything was really completely straightforward. But now we don't know anything about our manifold except the Ricci bound. But that gives us good information. So we have more elliptic estimates. More sophisticated elliptic estimates. So if we have any holomorphic section, then kind of standard form, if we take the Laplacian and supergeneralized sense of its modulus, this is less than mod S, and the Laplacian of the size of the derivative is less than something, I guess Ricci over k plus 1 or something like that, times essentially that. So under hypotheses, these are both well, this is bounded. So essentially deriving from this volume bound, it's a well-known, well-established that if you have lower bounds on the Ricci curvature give control of the Sobolev constants. And then by it's called the Moser method, if you have an inequality like this, you can get from L2 information, you can get L infinity information. So Moser, Sobolev, give L infinity bounds on mod S and mod ds. So, should slightly speed up to get to the main point. No, a lower bound on Ricci. Everything's a lower, as long as the Ricci is more. Ricci being positive, maybe I should put minus. That's right. But in fact, in our situation, Ricci is one. It's Kähler-Einstein, so Ricci is 1. Yeah, it's actually back in our situation. But actually, positive Ricci is okay. So let's see. I wanted to say delta. Yeah, so I'm going to change what I wrote down here. So let's suppose that in our situation, we derive that the size of the derivative of our holomorphic section is less than some number c, which we can completely compute from the complete number. And let's suppose that this diameter is less than, say, delta double primed over 10 times c, or something like that. Then, see, the size. It's a bit. You need to be a bit fiddly, but let's not worry about it. On this, if we fix delta double prime small, this is the big prime, some fixed small number, then we have good estimates, provided delta prime is a bit smaller. So we can suppose, by just the same argument, that our section is as close as we like, L infinity norm, to the model, a radius delta double primed. by making delta prime very small to make the extra error term, and of course r very big, of course, as well. So, so we can suppose that when mod z is equal to whatever it was, delta double primed, we can suppose that the modulus of sigma is bigger than 3/4 or something. So if then just by integrating this bound on the derivative, we see that the section has a definite lower bound on its modulus over the whole of the interior region. I haven't really, you get the idea. So this is some of the, this is not directly applicable to our problem, but it's some of the basic argument. It's clear we could do, it wasn't important that we had this little ball that was a mystery region that we cut out. We could have cut out other kinds of sets and argued in just the same way, provided we have this, we can make this good cutoff, provided the codimension is, the real codimension is at least 2, essentially, so we have these good cutoff functions. Okay. So the last, so now I want how to of course I'm out of time as always, but we want to indicate how more or less this argument combined with a whole theory involving the Gromov-Hausdorff convergence, something that we can, and related matters, a theory developed by lots of people, Gromov, Shiga, Kolding, Anderson, Tian, other people, probably. But applying all that, we can, we're supposed to deduce a result. So how are we doing? So recall the Gromov-Hausdorff distance. Supposing we have two metric spaces, say Z1 and Z2, to say that the Gromov-Hausdorff distance of Z1 less 2 is less than delta, it's a positive number, that means that we can take the disjoint union, we can find a metric on that disjoint union which extends the metric on the given factors, and such that every point of, well, there's some number strictly less than delta, such that every point of Z1 is within that number of a point of Z2. So both Z1 and Z2 are delta star dense for some delta star less than delta. That's the definition. So essentially it means less than delta. And the basic fact is, well, first of all, in our result, we can reduce to the case. So let's see. So the fundamental starting point for this theory is that if we're considering metrics with Ricci curvature bounded below, then that's the set of such things is compact with respect to the Gromov-Hausdorff convergence. So essentially what that means is that we can reduce our problem to saying we have a sequence xi of manifolds of the kind we're considering, which converges in the Gromov-Hausdorff sense to some limit x infinity. With some argument, I mean, essentially. So let's immediately go to that point. So this is just a, I mean, initially this is just a metric space, but actually a great deal is known about it, and that's what we want to use. So each point of x infinity, we have a theory of what's called tangent cones. We can consider rescaling, so we can consider taking that as a base point and rescaling the metric around that point, and the compactness theorem applies to such based rescaled versions. So taking any sequence of rescalings, we can take a a subsequence such that we get convergence. And the deep theorem says that what we will converge to will be a metric cone. So we get the notion of a tangent cone. There are many subtleties. For example, one is that these tangent cones are not known to be unique in all situations, but they exist. So this, in our situation, this will be in the sense of a generalized Ricci flat space, because we started with bounded Ricci curvature. When we scale up, the Ricci curvature will go to 0. And there are three cases. We're either going to have C3, or we're going to have C times a simple kind of quotient space. Gamma is a finite subgroup of U2. Take this quotient space. Or we're going to have the cone on some five-dimensional object, which doesn't split off any trivial factor. So in this case, the theory says that actually what we've got is a smooth point, and we get C. In fact, we get with this, the convergence is C. If we have such a point, the convergence here is in C infinity, as nice as we would like. So that's straightforward. So maybe I only have time to talk about. So we need to understand. Let's just talk about this, a slightly simpler case, because time is running short. So lots of so in fact we'll take there are different ways of doing this, but let's say we'll take K will run over integers of the form D times 2 to the nu, where this is going to control divisibility, as you'll see, and this is going to be our scale parameter. We always jack up the scale to make things better. So you'll see why we do that in a moment. So supposing we have a point P with this tangent cone, what that means is that if we scale up a very small ball in X infinity, it looks close to the unit ball in this model space. But on the other hand, so we take a small ball, say B P of R, close, say B of P, close to the ball in, the unit ball in C times C2 over gamma after rescaling in the obvious sense. In the Gromov-Hausdorff sense initially, but in just the same reason as here, for the smooth points of this thing, we can suppose it's close in C infinity. So let's draw a picture of this is C over gamma, C2 over gamma, C. If we remove a tube around the singularity, we could take a ball here. We can suppose we're actually close in C infinity on this region. And we can make this as small a tube as we like, and we can make the diameter of this as small as we like. So what do we have here? Here we have it's just on the smooth locus of this. We take the trivial holomorphic, so let's let lambda with a trivial holomorphic line bundle. But with metric e to the minus, in the obvious sense, more the same, essentially the same. In the obvious interpretation, we take the Gaussian metric, just as before. That has the correct curvature. So our line bundle, well, let's just leave out this little L, or L to the K or something. On the smooth subset here, this line bundle converges to a line bundle with the same curvature as this in a natural sense. So LK tensor L star tends to a flat line bundle on the smooth part. So that could be a problem because this is just given by representing a map from the fundamental group to the circle. For suitable gamma, there are such maps, but they're only going to be a finite number. This is a finite group. It's a subgroup of U2. It's a finite group. So by taking a dth power, we can always suppose they're trivial. So by choosing D sufficiently large, we can always arrange that this flat line bundle is trivial. By volume comparison, it is controlled, yes. By applying our Bishop-Gromov comparison, gamma couldn't be too big because the volume would be wrong. So in fact, we could write down what D would be explicitly, if we wanted, from a priori. But this is where it comes in. The argument by... this could be plus or minus 1. We take an odd k, it wouldn't work, but we just say we'll take even k, and we won't see this problem. So actually, this is trivial. So we can, time's running out, so we can suppose L to the k is identical with lambda, essentially, on the smooth locus. So now we can just do, we have just the same picture. We don't care about whether it was C2 over gamma or C2 at this point. We do just the same thing as we did before in our model argument. We have we construct a holomorphic section. We have a bound, blah blah blah. So see what we're going to do. We're going to do this not on the singular space. We're going to do this on the xi, which is very close to it for a large enough I. So what we conclude, trying to hurry things to a conclusion now, but this is really the main point, so we're almost there. So we conclude, I should say, this is the story for this one. There's substantially more work to do for this story, but obviously there's no time to talk about that. What we conclude is that for all p in x infinity, exists a ball, or exists some r equals r of p, and epsilon is equal to epsilon of p, and say nu is equal to nu of p, such that we have a holomorphic section holo. What do we say? We have rho for our manifold xi. This k is bigger than epsilon for points at points x in xk with the distance with respect to this extended distance function to p less than, what do I want to say, r. So we imagine we fix this metric on the disjoint unions extending the. So we know how to talk about the distance between points in the limit and points in the before we got to the limit. So we're saying for all points, as it were, close to this point, we can construct a thing with a definite lower bound. So what's the point of doing it this way? See, what you now see is that what we do is we get it for some particular large nu. What we get, but we don't. You might immediately worry about getting bigger. But we can always take powers of this section. We have these L infinity estimates and L to, so we get, if we take a power, we get some estimate. The estimate gets worse, but we get some estimate. So we can replace this by nu bigger than or equal to nu of p. So for all sufficiently large nu, we get some, what am I saying, epsilon of nu p. I think I said that right. It's a bit tricky to get all the things, but you'll get the idea, even if it's not exactly right. So now what we use is the fact that this thing is compact. In general, this is a compact space. So all we do is we cover x infinity by the balls of radius r over 2, r of p over 2. But obviously, but by compactness, we can take a finite cover. By balls b of, say, p alpha, r of p alpha over 2. And now let's suppose that the distance, we can take I so large that the distance of it is less than the minimum of these r of p alpha over 2 also. So now I claim that we have this estimate in xi, because if I have any x in xi, have I said this right? Almost certainly go wrong, but let's see. There's some x infinity with distance x infinity x less than r over 2, but there's the distance from x infinity to some p alpha is less than r over 2. So x lies inside one of these good regions which we've understood, once we take nu bigger than the largest of all these nus. So I should stop. I've slightly gone over time. But this is the main point of the argument, to combine this Hormander technique with all this convergence theory. That's what we hope proves the result. Maybe what I should have said, that what this, I'm not sure, perhaps I'll answer that question. I think you're trying. What it indicates is that we have embeddings of these things in some large projective space, and we can embed this thing in projective space as an algebraic. That's what it indicates. Well, in some singular sense, but at least it's an algebraic object. That's the. Well, you could, of course, resolve this. You could do that. I mean, you could resolve. I mean, the model case would be a singularity like that. Of course, you could resolve. Yeah. But maybe more indicates that there's a connection between these cones which appear in the differential geometry and the kind of algebraic geometry study of singularities and things like that.
You're staying away from the singularity of the cones, right? So algebraic embedding. You actually know that when you get closer to the I want to call them vertices, but they're not. I mean, but at the vertices of the cone, you know that this is actually an algebraic.
That's the kind of thing one should be able to prove, or something like that. But we have. just like we discussed in the model case, we can also, at least if our model is an algebraic variety, an affine algebraic variety, we can embed these. We can produce holomorphic functions locally on our xi to embed them as. But yeah, there are subtleties to work out to say something precise. But certainly one would expect that. The whole picture is an algebraic description, ultimately.